Welcome back. This is the continuation of the full work solutions of the Nature of Light worksheet 4B, focusing on length contraction and relativistic momentum. We have now completed the first part of this worksheet all the way down to question 9. So this worksheet is going to be 10 onward. Okay. In 10, we're going to be introduced to a concept which is often misunderstood in when we talk about relativity, relativistic mass. Relativistic mass comes as a product of its momentum. We know that now momentum is actually equal to, the relativistic momentum is equal to gamma times the normal momentum, which is a Newtonian momentum, which is gamma times mv. Okay. Now, what this is you can consider it to be gamma times m times the velocity. So often we think about this term here, gamma times m, as being an increase in mass. Now, physically, there is no increase in mass. It's just simply that we have this understanding of mass. Mass, the total mass, is equal to the sum of its components plus, as Einstein told us, its energy equivalent, which we know is the energy, could be potential or kinetic, divided by c squared. If this is kinetic energy, it adds to our total mass. If it is potential, it subtracts away from our total mass. So starting from this point here, which is our mass equivalency formula, we know that if we take this across to there, that the actual physical total mass that we measure would be equal to minus the component's mass, that's the mass when they would be at rest without any energy input, would equal E on c squared. Now, if the energy is kinetic energy, then we can think about this here as being not E anymore, but K. So firstly, we get mass total minus mass rest. This would be seen as a change in mass. So I've got delta M here. Replace that. So this here, total minus rest mass, is equal to delta M. And that would give us E on c squared, as Einstein told us. But if E is coming from kinetic energy, we get, therefore, delta M would equal K on c squared. And multiplying that up, we get K equaling delta M c squared. So the kinetic energy of a particle traveling at relativistic speeds would be given by this formula here. Now, what is the change of mass? Well, we just mentioned that gamma times m would be perceived as the change in mass. So the change of mass will be the new mass, the mass which is happening because we are moving, minus the mass over here, which is the rest mass. That was the change of mass times c squared. So it's delta m c squared. So it's delta m c squared. So I'll just write that out. So K equals delta m c squared. Okay. And delta M would be the new mass, which is delta M times 0, minus the old mass, which is that, okay, which is, I shouldn't say old mass, that's the original mass. And this is what we consider to be the new mass, times c squared. Expanding that in, you get delta M naught c squared minus M naught c squared. So that's what this formula here is trying to tell us, okay? Which then, if we were to take the m naught c squared, because it is common to both, this gives us an expression for kinetic energy. And that means that kinetic energy is given by m naught c squared gamma minus 1. Okay. At low values of gamma, this factor becomes gamma minus 1 becomes significant. But as gamma gets really, really, really big, as velocities get closer to the speed of light, this becomes less of a deal. Okay. Now, the upshot of this is it's easier simply to memorize this formula. We don't want to derive it each time. The kinetic energy of an object traveling at relativistic speeds is given by that. If we are talking about kinetic energy at lower speeds, please always use a half mv squared, where this v here is simply the velocity of a normal velocity, nowhere near the speed of light. So we use this formula only for day-to-day non-relativistic set settings, and this one up here to calculate the kinetic energy of high energy, high moving protons and so on, very objects which are going, at very high relativistic speeds. Okay, rightio. So that being said, now let's go and answer question 10. Right. So a proton's rest mass, now this is just, rest mass is simply the mass that we would observe it to be if it was in the laboratory and we haven't accelerated. We're taking that proton and we're moving it to a velocity of 0.99, and it's going to be in the Large Hadron Collider, the LHC. Okay, so you'll often see that abbreviation for that. Let's calculate the momentum of the proton at this speed. So 10A is just a momentum calculation. So the momentum at a relativistic velocity is going to be gamma, its normal momentum, or we could just write gamma mv. I often just go straight to this one here. Okay. We need the gamma factor for this. So the gamma would equal 1 over 1 minus 0.99 squared. And I've lost my calculator. It's somewhere under this part. There it is. Paper. So it is 1 over the square root 1 minus 0.99 squared. And it's 7.0888. Okay, once again, I'll keep that on my screen. So that's the gamma. Oops, put it in the wrong place. So multiply by the mass of the proton at rest, which is 1.673 by 10 to the minus 27. Multiply by the velocity, it's 0.99 times 3 by 10 to the 8th. Okay, I always keep on getting them too close together there. Right, okay, so let's do that multiplication. So there's the gamma factor multiplied by 1.673 exponent negative 27, multiplied by the velocity, which is 0.99 of light, and we get its momentum as 3.52 by 10 to the minus 18 Newton seconds. Okay, so that's 10A. 10B is asking us now to calculate the kinetic energy. So we're just going to simply use the final formula. K is equal to m naught c squared gamma minus 1. Okay, so m naught is its rest mass. This is what it would be measured if it was stationary. So it's 1.673 by 10 to the minus 27, multiplied by c squared, which is 3 by 10 to the 8th squared, and multiply all of that by the gamma factor, which is 7.0888 minus 1. Okay. So putting that all together, let's just get a nice place to put 1.673 exponent negative 27 times 3 exponent 8 all squared, multiplied by, open bracket, 7.0888, one more 8, minus 1, close a bracket, and we get 9.16 by 10 to the minus 10, and this is joules because it's kinetic energy. Okay, so it's much simpler if you just simply use this formula, have it memorized, rather than going through the entire process of deriving it each time. Okay. C says calculate the rest energy of a proton. Okay, so what is rest energy? Well, the rest energy is the energy equivalent using the energy equivalence formula. So we know that E equals m naught c squared. So m naught is the rest mass times c squared. So this would be the energy equivalent if all of this was if all of this energy, this mass over here came from kinetic energy or a form of energy. So let's just use m naught c squared, or just mc squared. So that's 1.673 by 10 to the minus 27 times 3 by 10 to the 8th, 10 to the 8th squared. So in other words, it's simply this part of the expression. Okay, and let's calculate it one more time. That is, I'll just move that up. There we are. 1.673 exponent negative 27 times 3 exponent 8 all squared, and the energy equivalency is 1.5 by 10 to the minus 10 joules. Okay, I think there's a few more decimal places in the answer. It says 5057 on my calculator. Okay, rightio, let's continue on. Question 11. Question 11 says, let's get it there, a spacecraft with a rest mass of 150,000 kilograms is traveling at this one here. What's its kinetic energy? Well, it's a 0.99, and we calculated the gamma factor for a 0.99 in the last one. I'm just going to use that. So the gamma factor for 0.99C is equal to 7.0888. Okay, and we're asked to find its kinetic energy. So kinetic energy is m, let's see, it's mc gamma minus 1. Just put little mc squared up there, so I'm missing. So that's m naught there. So that's all it is. So this is its rest mass. This is the normal mass that the craft would be if we were measuring it on the surface of the Earth when it's stationary, times c squared, which is 3 by 10 to the 8th squared, times gamma minus 1, which is 0.888. So I've already taken 1 off that because we know that it used to be 7 point. Now it's going to be 6 point. Okay. Doing this multiplication out, 150, 122, times 3 exponent 8 and square that, times 6.0888, and we got 8.222 by 10 to the 22, and talking about kinetic energy, it's joules. Okay. Right, moving on. Question 12 now. Okay. Question 12 is an atom of uranium has a rest mass of that many kilograms, and it has a diameter of 156 picometers. The atom is accelerated to this. Okay, so we're going to calculate its rest energy. its observed diameter when it's moving, and its kinetic energy when it's accelerated. Okay, so rest energy. So rest energy is simply given by E equals mc squared, where this is the m0 is its rest mass. So that's going to be 3.9 by 10 to the minus 25. It's given in the question, times 3 by 10 to the 8th squared. So this will give us 3.9 exponent negative 25 times 3 exponent 8 squared. So that's 3.51 by 10 to the negative 8 joules. Okay. I think the answer has 35.1 by 10 to the minus 9 joules using the engineering units. That was A. I'm going to pop down straight to C. C says calculate its kinetic energy. Okay. The reason why I'm doing that is you'll see there is a similarity in the working between these two. So we've now taken this uranium atom and we're accelerating it to this value here. So we need to find its gamma factor. So the gamma would equal 1 over the square root of its 95% of the speed of light. So it's 0.95 squared. And 1 over square root of 1 minus 0.95 squared. And that's 3.20. I've met this number quite a few times. I should have looked back. Okay. Now, the kinetic energy is equal to m naught c squared gamma minus 1. Okay. And you should recognize this part here. That is that. Okay. So we've already got this little section in here. It's there. So taking my rest energy, multiplying my rest energy by gamma minus 1, I get the kinetic energy. So is 3.51 by 10 to the minus 8 multiplied by gamma minus 1, which is, well, if its gamma is 3.2, then it'll be 2.2. So taking the last answer, and multiplying that by, so this is, I'm taking 3.51 by 10 to the minus 8 and multiplying it by 2.2. The kinetic energy in this situation is 7.72 by 10 to the minus 8 joules. Okay, or it's 77.2 by 10 to the minus 9 joules. Okay, I think I might have a 3 in that position in the answers. That's simply because that was rounded there. Okay, rightio. Now we can go to B. B is calculating the observed diameter. Okay, so this observed diameter, remember, if we start moving at 0.95 C, this is our uranium. This uranium atom sees itself as having a diameter of 156 picometers. But we see this as being length contracted. Okay. So the length at velocity is equal to its proper length divided by gamma. Okay, because we're seeing a contracted length. So its proper length is 156 picometers divided by 3.2, which is the gamma factor. Remembering, once again, I remind all the time, because we are using this formula as we found the gamma separately, we can use units up here because this is a ratio. And ratios do not change units, they respect units. Okay, so that's simply going to be 156 divided by 3.2. That will give us 48.75 5 picometers because the units are respected. I think, once again, because I have, it's not exactly 3.2 here, and I've just done that, the answer might have no 5 there at the end. Okay. Rightio. And finally, let's do question 13. Question 13, a proton is traveling in a circular, I should put it in front of you. A proton is traveling in a circular hadron collider with a radius of 500 meters, and it's traveling at that. What is the strength of the magnetic field acting perpendicular to the motion needed to constrain the protons in this path? Okay. Actually, I'm going to stop here because this is going to be quite a long process. I'll start with the next video at 13. Okay.